Hey, good afternoon. Today we're going to be talking about how we can use the critical point of a material and use that to determine our A and B parameters that are in the van der Waals equation of state. And where that's going to help us get to is being able to see and get and arrive to the compressibility factor of a material. And the compressibility factor is the deviation that that material takes in its gas behavior from what it would be taking as an ideal gas. And why would a gas be deviating from how it's able to be understood as an ideal gas? And van der Waals helps us understand that. And so a little bit of just background with what's going on here is molecules. Van der Waals helped by experiment and theory determine that molecules will spontaneously induce dipole-dipole interactions. And so what will happen is the electron density in a specific molecule will shift and will fluctuate. And so when that happens, and this happens spontaneously in molecules, is there's temporarily a partial positive and a partial negative at those parts of the molecule. And when that happens, it creates an attractive force for surrounding molecules. Now, in the ideal gas law, temperatures are either so high where the energy is causing the molecules to just move so quickly or have high enough energy states where they don't really interact with other molecules, and so we're not really concerned about these van der Waals forces, or at pressures where they're not going to be compressed in and packed in together. We're able to use the ideal gas law. But there's a lot of chemical engineering situations and scenarios where we have to deal with high pressure situations. One case in point would be the Haber-Bosch equation, where being able to create artificial fertilizer, and that requires a very high temperature in order to get gases to produce what we need. And so there's a lot of chemical engineering equations that are in syntheses and processes that are very important that require high pressure situations. And the reason that we have to deal with van der Waals here is because if we think about it, when we get into a high pressure situation, we're really compacting in all this same amount of molecules, but into a really tight space, meaning they have a lot less room to move around, and they sort of bouncing off each other. And when they get really compressed in, those van der Waals forces with the spontaneously induced dipole, they start to become a lot more relevant and attractive in their power. And so that's where we have to be able to take this into account. And so let's go ahead and take a look here, a little bit of our pressure and volume diagram, and understand a little bit of what's going on here. So first, let's go ahead and write out van der Waals' equation, where he took his equation of state. And so we've got our pressure, and we're dealing with R times T, and the temperature here, and then the volume, and it's going to be a volume at a specified state here, minus B minus A over V squared. A couple things to note here is this right here, the volume is the excluded volume. And what is it that we're excluding? Well, it's the mole, it's however many molecules that we actually are considering in the substance that we're evaluating. So a nice analogy that we could use would be if you're hopping onto the school bus to get a ride, and you walk in, and the entirety of the inside of the school bus would be our VS here. That's our specified volume at that state. Now, you're not just riding this bus alone. There's a lot of other kids that have already been picked up, and so those kids are already taking up other seats inside the school bus, and they're already taking up space, right? Just like molecules in a container, you can't have two molecules taking up the exact same point in space in time at that same exact space at that same exact time. So they can't be on top of each other. And so I can't like mesh in and merge in with a student on the school bus. And so there's already spots that are on the school bus that are already taken up. And that would be our excluded volume here, which is what we're considering. And then the A right here, this is the attractive van der Waals forces between the molecules. And if we want to think about why is it minus here? The reason it's minus is if we think about when the molecules are being attracted, they're coming in closer contact with each other. They're getting attracted towards each other, meaning they're bouncing off the sides of the wall less often. And if they're bouncing off the sides of the wall less often, that means there's less pressure that's being pushed on and outwards towards the container. So that's what these are our A and B parameters that we have to be able to consider. And this is what's happening and these situations where it's no longer being able to be considered as an ideal gas. And so that is what is at stake here is we can't just take a gas and treat it as an ideal gas because of these van der Waals forces that happen when the molecules start to get either higher pressure situations or lower temperatures, and the van der Waals forces really start to actually come into play. So coming back to our pressure and volume diagram here, this solid line, this nice solid line right here, this is the region right here where the vapor and the liquid are in equilibrium. And so we're these dashed lines here we've got it's an isothermal situation that we're considering, meaning that the temperature is going to be staying constant, but the temperature might be staying constant, but the pressure and the volume are not. So the temperature here, this is T greater than the temperature at the critical point. Here is our temperature exactly at the critical point. And then we'll talk about the critical point in just a second. And down here, here we have because this is the liquid and vapor in equilibrium, when we're at this part, for example, or anywhere in here, this dashed line in here, we'll start with here. When the pressure is right here, the volume is at a specified point in its liquid form. Same thing over here is when we are at this point with our volume at a specific volume, and at the same pressure point, it's going to be here in its vapor form at that specified volume. But what about everything in between here? Well, everything in between here doesn't actually exist in nature. So it's the material, the water, for example, that we're going to be looking at, is not in this intermediate thing where it's like this combined, conjoined liquid vapor intermediate phase. What actually ends up happening is when it's at a pressure point here, it's going to split the volume. And so some of the volume is going to be in the liquid phase, and some of the volume is going to be in the vapor phase. And what is incredible to look about here, and this is going to be what gets us to our critical point, is the volume gets split. But as the pressure increases, because as the pressure increases up this line, we start to see that this line of equilibrium, the volumes start to become a much smaller difference in the volumes that each state is taking up. So as we keep getting closer and closer and closer, and this is our critical point here, right where we see our C, as the pressure is increasing, the amount that's in the liquid phase, the volume that it's specifically taking up, is getting ever closer, right, to the volume that is in the vapor phase. And so the volume, the difference in volume that both are taking up, get closer and closer and closer to the point where they finally hit this critical point. And the critical point, dealing with a pure substance in a closed system here, the critical point is where the material becomes indistinguishable between a liquid and a vapor. And so another way to think about it would be the refractive index of the light. When it's hitting this compound now at this critical point of pressure and temperature and volume, is there's no difference between the way the light refracts off of the liquid and the vapor. They become indistinguishable, one of the same. The properties at the critical point are the same. And so they become this indistinguishable property here, or material. And so that is when we've reached our critical point where the volume at the liquid phase is exactly the volume at the vapor phase, right here at the critical point. And so why does that help us? And what does that have to do with the van der Waals equation of state, which we saw right here? Well, it's not skipping over. Oh, there we go. It's just lagging a little bit. Well, what is incredible here is that we know, and I'll draw in here, we're dealing with our temperature at the critical point. We're dealing with our volume, our specified volume, at the volume that it is at the critical point. Same thing with the pressure at the critical point. We are able to have tested these things experimentally. And so now we know our pressure at the critical point of a substance. We know R as a set value. We know the temperature at our critical point and our volume. And so that all that is left for us is, I should have also written this right in here. There we go. Okay. What we're left with now is A and B as our parameters. So let's go back to our pressure and our volume diagram. What is fascinating here at the critical point is that it's at the max peak. The first derivative of this equation is 0. There's no rate of change. The liquid and the vapor have become indistinguishable. They become conjoined. They become one and the same, so to speak. And so the first derivative here is 0. And then if we look here, the second derivative, look at this. This is concave up. Everything preceding the critical point. This is concave down. Immediately following after the critical point. So these are inflection points right at the critical point. And so we know that we're able to set our derivative, our first derivative and our second derivative to 0 at the specified volume, which in this case happens to be the temperature at the critical point and the volume at the critical point. And so now what we're going to do here is find the first derivative and the second derivative from our van der Waals equation of state. And because we're able to set both of those to 0 from what we found from the pressure and volume diagram, that's going to allow us to have all the information we need to then be able to solve the parameters A and B. And so let's go ahead and walk through that now. So starting with the van der Waals equation, we're going to take that, and here we have it at P equals R, temperature, volume, minus B, minus A over V squared. And we're going to evaluate it at the critical point. The reason we're going to evaluate it at the critical point is because we know what our volume is, we know what our pressure is, and we know what our temperature is, all at the critical point. Once we are able to then solve for the first and second derivative with that, that's going to allow us to make predictions about the behavior of the gas at any other point. For regardless of the temperature, we're going to be able to know the pressure at any other point, and we're going to be able to make predictions that are going to be really useful even when it's not acting according to an ideal gas law state. And so let's go ahead and move forward with that now. So we're going to go ahead and label this and specify all of this is happening at the critical point. So let's go ahead and start now with the first derivative. And we're going to take the partial derivative with respect to, well, the partial derivative of pressure with respect to volume. And this is all happening where the temperature is equal to the temperature at the critical point. And that is going to end up equaling 0. And then the second derivative is going to be partial derivative of pressure with respect to the volume. Again, where the temperature is equal to the temperature at the critical point, and that derivative is also going to be set to 0 because that's where the second derivative showed the inflection points when set to 0. So now we're going to take the, take the derivative of this here, and that's our equation of state. We're going to take the first and second derivative of that equation. And so let's go ahead and do that now. So here we have the first derivative is going to be, what is that? Negative R, temperature at the critical point, volume at the critical point, squared minus, no, not minus, that would be plus 2A, by the way, volume at the critical point cubed. Now our second derivative is going to be 2 times R, temperature at the critical point, volume at the critical point minus B, and that's going to be cubed minus 6A, the volume at the critical point to the fourth. So now what this allows us to do is we're going to set both of these equations. Because they're set to 0, we can go ahead and just bring this equation over to the other side, this equation over to the other side. And so let's go ahead and do that now on our next page here. So what was that again? That was R times TC over C minus B. What would that be equaling? So we had minus 2A, so positive 2A, bringing it to the other side, cubed. And then, so that's at our first derivative. Second derivative, we had 2 times RTC over C minus B cubed, positive 6A over VC to the fourth. And so now we can take the inverse of the second derivative and multiply that with the first derivative equation. So what we're doing here is VC to the fourth over 6A. Here we're taking VC, making sure it's just all showing up on the screen, 2 times RTC. And these we're multiplying right here by both of these sides. And so that, what is that going to leave us with? We're going to have, let's see, that leaves us with, when we multiply all of that, this cancels out. Not there. Well, this all cancels out down here. That all becomes 1. But up here, we're going to end up having VC minus B, because this is cubed, divided by 2 equals, and then here we got VC to the fourth, so that goes over 6A, so the A goes, and then, so VC over 3. There we go. Okay. Now we can go ahead and set this to solving here. So let's go ahead and multiply 3, and then we can multiply this other side by 2. Well, we'll do this here, so we've got equals 3VC minus B minus 3B over 2 equals VC. Let's just go ahead and rewrite that. This is 2 VC. And then that leaves us with VC equals, did I do that right? Times 2 VC equals 3B. I did, yes. Sorry about that. B equals, because I was throwing myself off, I was solving for volume at the critical point, which we already know, forgot that the whole point of this is to solve for B. So B, very simple now, is equal to volume at the critical point divided by 3. And so let's go ahead now and solve for A here. And now that we know A, or now that we know B, we can just plug B into either one of our derivative equations. So we'll take our first derivative equation and plug B in, plug in B. It's not showing up, there it is. Plug in B. And so Now, what that leaves us with is bringing in, so now we're going to have, what do we have? Our first derivative equation was negative RT times TC VC. Bring in the B, swap in VC over 3. Okay, and then let's go ahead and let's go to this one here, right there. So let's solve for this right there. So RTC TC equals VC minus B squared equals 2A VC cubed. Now we know that B equals VC over 3, so we can plug in our B there, which allows us to take and have, let's see. So what we're going to do is plug in our B, which is the volume at a critical point, divide by 3, and we're going to plug that into our first derivative here. And so here is our first derivative right there, and B is what we're going to plug in. And so in order to do that, we've got RT VC minus VC over 3 squared equals 2A VC cubed. So now we have to simplify the denominator, which is going to lead to pulling out that 3. So that's going to lead to 3VC minus VC. This whole, sorry, what I'm doing here is I'm just dealing with the denominator at the moment. VC, this whole thing is going to be squared, leading to 2VC over 3, this whole thing getting squared. Then, so this situation, we're going to then bring this, start this over here, to just 2R times temperature at the critical point over 4/9 volume at the critical point equals 2A at the critical point cubed. So then let's go ahead and just take this fraction and get that so it's simplified. There we have B worked in to the equation. And so now let's go ahead and transfer this over to solve for A. And so what was that again? That was 9/4 RTC divided by TC 9/4 RTC over VC equals, what was it? It was 2A divided by VC cubed. Okay, so now let's just go ahead and multiply this and that by both sides. There we go. That will cancel out, that will cancel out, leaving us with VC squared on top. Is that right? Did I miss something? Oh, VC squared. This should be VC squared. I forgot to carry that over when I did that, due to the square right here. So we got that inputted now, meaning this needs to be VC squared. So this goes, so now we're going to be left with 9/8 RTC VC equals A. So that is our parameters for A solved, and B again is VC divided by 3. And so what this allows us to do now is to move forward with discussing the compressibility factor. And so again, the compressibility factor is, and we'll label that here as Z, And so Z is our compressibility factor. I'll start a new page here. And the compressibility factor, again, is the deviation that our gas is going to be taking from how it would behave if it were an ideal gas. And so what does Z equal? Well, Z equals P times V divided by RT. Well, that is the ideal gas law, meaning that when a gas is actually operating as an ideal gas, our compressibility factor is 1. So we need to know the ratio of the compressibility factor when it's not behaving at as an ideal gas. And because we're going to be dealing, what we're solving for here is the compressibility factor at the critical point to allow us to make predictions outwards. We're going to go ahead and solve what is the compressibility factor at the critical point. The R remains constant. So what is this ratio right there? And so let's go ahead and solve for that now. Again, we have our pressure at the critical point equals, according to van der Waals equation, minus B minus A at VC squared. Okay, and so now that we've solved for A and for B, what this allows us to do is plug and play our A and our B that we just solved for, put it into our equation here, and that's going to give us our compressibility factor, and it's going to show us the ratio at which the deviation happens when what the gas is operating at instead of as an ideal gas. And so let's go ahead and do that now, leaving us with the pressure at the critical point. Let's go ahead and plug in here, make sure we can see it. Let's bring this up here. So this is going to be equal to, when we bring in our B, remember B was VC divided by 3, and our A is 9/8 RTC, so let's see here, 9/8 RTC VC over, and then again times VC squared. So then, what does that leave us with? Let's go ahead and again factor this out. So when we factor out a 3, when we factor out 1/3, my apologies, 1/3, we're left with 3 VC minus VC, leaving us with 2/3 VC on the bottom. And this is starting to get a little bit messy, so let's go ahead and bring this to the next page. Well, let's just real quick solve. The denominator is going to be 2/3 VC, so when we bring that to the numerator, we're going to be left with, just write this over, just flip the denominator, multiplying the bottom and the top by 3/2, and so now we've got RTC divided by VC. And then, what do we have for our A? Is going to be 9/8 minus 9/8, our temperature critical point, and then VC squared. Is that right? Yes. And so, did I miss something along the way here? I did. We still had a VC up here, so let's go ahead and just take that out. And so now we're just left with, now we're just doing some simple algebra to bring this out to be. So we'll pull out our similar variables here. So that's 3, 2, minus 9/8. Let's go ahead and, which leads us to RTC VC is going to be, what is it, 12 minus 9 over 8, which leads us to 3/8 RTC VC. And so this is pressure at the critical point. Now we will recall that because our compressibility factor at the critical point is equal to pressure at the critical point, temperature at the critical point, back from here, this equation right here, R times volume at the critical point, all we're doing is bringing out, we're just re-manipulating this with this, which leads us with having a compressibility factor of 3/8. And so now that allows us to see the ratio that is happening with the actual behavior of the gas when it's at a high pressure or a low temperature, and when it's acting in states that are outside of the ideal gas range. And this right here is our compressibility factor ratio that we have solved. And that was from using van der Waals equation of state, setting the first and second derivative equations, or first and second derivatives to 0, solving for the parameters a and b, and then working that back in to find our compressibility factor.